Well, welcome back. The title of this lesson is called the Binomial Theorem. This is part 1 of 2. So the purpose of the binomial theorem is to be able to take a binomial, that means a parenthesis with two terms on the inside, and raise it to a power. So for instance, a plus b to the power of 2, a plus b to the power of 3, and so on. Now, if you followed on in sequence here, you'll know that in the last lesson we already learned how to solve these kinds of problems before. We used Pascal's triangle in order to expand binomials like that in the past. And that method works great. You have to create Pascal's triangle, which is very simple to do. You can go into that lesson and see how we did that. And the triangle gives you coefficients that go into your answer. And then we learned the methodology to construct the answer, to expand any binomial once we know Pascal's triangle. It worked great. It works great. The only problem with it is that what if I want to expand a binomial much larger power? Instead of a plus b squared or a plus b to the third, what if I want to do a plus b to the 50th? Or what if I want to do a plus b to the 1000th power? Well, then I have to make an enormous Pascal's triangle with, 1,000 rows or something, and it just gets very cumbersome to do. Computers can do it, but by hand it becomes very cumbersome. So the binomial theorem is an equation. It's a single equation that allows us to calculate and expand and multiply out these powers of binomials no matter what power we have. Now, the problem with the binomial theorem is when you flip to most textbooks, you look at it and it's really scary looking because it has a lot of terms and a lot of exponents and a lot of letters and all these things. It's very simple to make mistakes. So what we're going to do in this lesson, first of all, is I'm going to write the binomial theorem down on the board. I'm going to explain what it really means, what the different parts of the equation really are telling you. And then we're going to do some review of factorials, which is going to help us to be able to use this equation, because factorials are everywhere in the equation. And then we're going to solve some problems at the end that are going to give us concrete practice with using it. Then we get on to the next level, the next lesson. We will crank up the problem complexity a bit so that we take the training wheels off and start using the binomial theorem for more complicated problems. So let's do a little bit of motivation first. Before we actually present what the binomial theorem is, we have done these kinds of problems in the past, but I just want to refresh your memory what we're basically doing here. If we have a plus b to the power of 2, this is the quantity a plus b squared. That means a plus b times a plus b. And you can do FOIL, F-O-I-L. You multiply all the terms, add them all together, and what do you get as an answer? When you simplify this answer, you get a squared plus 2 times a times b plus b squared. We know how to do this with multiplication. It's not too hard to do, okay? Now, let's do write down a similar. The cousin of this one is a little more complicated to do by hand, but still manageable. And I did this in the last lesson as well. A plus b to the power of 3. That means a plus b times a plus b times a plus b. And you can cross multiply all of those terms and add them all together. And when you simplify that final result, this is what you get. A cubed plus 3a squared b plus 3ab squared plus b squared. Now, one thing, sorry, not b squared, b cubed at the end here, b cubed. A couple of things I want to point out. I mentioned all of these things in my last lesson when we did this using Pascal's triangle, but I want it to be in the forefront of your mind. When we expand these things, notice how this is a square, and so because of that, every term in here, the exponents of the terms add up to a 2. Here, the exponent is a 2. Here, the exponents are 1 and 1, so when you add them up, the total exponent here is a 2. Here, the total exponent is a 2. Here, when the binomial is cubed, you have a total exponent count of 3. These exponents add to 3, these exponents add to 3, and these exponents add to 3. That's always going to happen. Whatever you do when you expand a binomial, all of the terms, the exponents have to add up to whatever the exponent is you have here. Secondly, these coefficients 1, 2, and 1, and then 1, 3, 3, and 1, these coefficients are the coefficients that come from Pascal's triangle, which we've done in the last lesson. If I expand a plus b to the 4th, or a plus b to the 5th, or a plus b to the 6th, then I look in a different row of Pascal's triangle, and I'm going to get these coefficients here so I can construct the answer. The final thing, notice the pattern in the answer here. Look at this one. The first term is just this first term here squared. Then for the next term, forget about the numbers. The next term, a goes down by 1 power to a first power. The b is b to the 0 here, which is 1, and the b goes up to a power here. And so every time I move through it, that's what happens. A goes down by a power, B goes up by a power. A goes down by a power here to a to the 0, and B goes up to a power to a 2. Here it's cubed, so the first term is just cubed. Here I go down a power to a squared and up a power in B, down a power to a to the first, up a power to b squared, down a power to a to the 0, which makes it disappear. B goes up a power to b cubed like this. So that's the general pattern. Now what we are going to discover is the binomial theorem is going to take care of all of this stuff for us. It's going to generate all of these coefficients no matter what power I'm trying to expand to. And it's automatically going to get the correct exponents in the correct locations, just like we've done in the last lesson. So what I want to do is leave these on the board, because actually we're going to solve both of these problems using the binomial theorem in just a minute. But before we get there, I need to write down what is the binomial theorem. Remember, the only purpose of it is to be able to do calculations like this, expand binomials. What if I have a plus b to the 67th power? What would that thing be? So here's what the binomial theorem is. It goes something like this. A plus b to the power of n, because I don't know ahead of time what power I have. I'm going to stick that in here. And to calculate that expansion, this is what it is. It is the summation, so you have this sigma here. I'll explain this in a second, but you have k is equal to 0 going up to n, and here's what you're summing. It's a really large expression, n factorial divided by n minus k, close parentheses, factorial, but then again multiplied by k factorial. And then over here you have a to the n minus k multiplied by b to the k. So let me just double check myself. A plus b to the n, sum from k to 0 to n factorial, n minus k factorial, a to the n minus k, b to the k. This thing is the famous binomial theorem. I told you it would look intimidating, okay, but really when you start solving some problems, it's just kind of a recipe that gives all these coefficients and all of these terms. Most books are just going to throw it at you and say, here's the binomial theorem, and go off and tell me what a plus b to the 10th power is. The problem is, if you don't know how to use the thing, then it's hard to do those difficult problems. So what we are going to do is break it apart, talk about it, and then we're going to solve these two simplest problems you can possibly have using this, so you know exactly how to apply everything. And in the next lesson, we're going to crank up the complexity a little more. First of all, what does this thing mean, okay? I want you to basically, for a moment, look at the big picture, okay? This part, okay, I don't want to put parentheses, I don't want to clutter it up, but all of this stuff in here, so I'm going to say from here all the way to here, this part of the binomial theorem gives you the coefficients. In other words, look up here. The coefficient of the first term was 1, then a 3, then a 3, then a 1. This calculational part, that's what generates these coefficients, right? If it's a different power, like to the 4th or the 5th power, it's going to generate different coefficients, okay? These parts over here, the a and the b raised to the powers like this, these generate the powers of a and b. In other words, you saw the pattern here. Cubed, then it goes down to a square, b goes up, then a goes down to a first power, b goes up to a 2. So basically, one of them is always going down and the b is always going up. So the first term in your parentheses is always going down in powers, and the other term is always going up in powers as you step through all the terms. All of that is taken care of by this term. So in order for you to understand that, I want you to first cover up in your mind. Don't even look at this. Don't even look at this part of it here. Forget about that. Just look at this right here. If I do a sum, notice the exponent is n. So let's just say that n is 3. So we're going to expand this one. So let's say n is 3. K goes from 0 to 3. So forget about this. Look over here. What you're going to have for the first term is a will be 3 minus k, but k is 0. So you have a cubed. But then b is just k, but k starts at 0. B to the 0 is 1, so there's no b term. And a is a cubed. That is the very first term here. And then when you step through it and make k equal to 1, you go through the whole thing again. Then you have 3 minus 1 means a is squared, that's this one. And then b goes up because k was 1. b becomes b to the first power. So as I step through the k, all of this stuff right here, all it's doing is generating this pattern where we start at the high power in the first thing, and it's going down that is because of the subtraction here. The second guy in the parentheses, in this case b, is going up, and that's because k is keyed off of, it starts 0, then 1, then 2, then 3, and so on, and it goes up like this. So this here is just generating the a's and the b's. That's all it's doing. This stuff in the front is generating these coefficients, which can also be used or looked at in Pascal's triangle. Now, in order for us to really be able to do binomial theorem stuff here, we need to do a little bit of review. And I'm trying to decide, where do I want to do? I think I want to do a few of them over here, actually. Okay, so we need to talk about factorials because we have factorials everywhere. I know you've seen this before, but I really want to review it to make sure we're all on the same page. If you have 6 factorial, what does that actually mean? It means the following. The exclamation point means 6 times 5 times 4 times 3 times 2 times 1. So literally, when you see this exclamation point, it means you start at this number and go down, 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 down till you get a 1, and you multiply all of them together. And when you multiply all these together, in this case, you get 720. So if you grab a calculator, put 6 factorial, you're going to get 720. Now, I know that you all know that, but here's what we really need to focus on. What if you have something like 5 factorial over 3 factorial? How do you handle that? Now, you might guess, and you could totally do it this way. You might guess that in the numerator, I'm going to go 5 times 4 times 3 times 2 times 1. I'm going to calculate that. And then this, I'm going to have on the bottom 3 times 2 times 1. I'm going to calculate that. And I'm going to divide those numbers. That's exactly right. You can always evaluate these factorials when they're divided by doing that. However, there's an easier way. Take a look at what the 5 factorial is. 5 times 4 times 3 times 2 times 1. And in the bottom, it's just a 3 factorial, so it's 3 times 2 times 1. Look at what you have here, okay? You have a 3 on the top and a 3. Everything's multiplied, so the 3's can cancel, and the 2's can cancel, and the 1's can cancel. So really, all of this is equivalent to just 5 times 4, which is actually 20. Now, we, by cancellation, eliminated half of the problem, and we just got 20. But if you get a calculator and you actually do 5 times 4 times 3 times 2 times 1, get that number, and then do 3 times 2, which is 6, times 1 is 6, divide by 6, you're going to get 20. If you go the long way, you get the same thing as you do with the cancellations. However, when we're using binomial theorem, notice that we have a factorial in the top, and we have factorials in the bottom. And because this is a sum, we're going to be generating lots and lots of terms with factorials in the top and factorials in the bottom. And because of that, you're going to waste all of your time trying to calculate all of those factorials in calculators. You need to start to look at division of factorials in a way that saves a little time. And that way is you need to start visualizing what is going to cancel out of the factorial like this. So let me give you a little bit more of a real example. What if I give you 100 factorial over 99 factorial? Now, the brute force way to do it would be 100 times 99 times 98 times 97 times 96 times 95, all the way down to 1. It would be something like this: 100 times 99 times 98 times 97, 6, 5, 4, 3, all the way down. So I'm going to just put dots here, times 1. All of that's going to be in the numerator. It's an enormous number. The bottom is going to be 99 times 98 times 97, 96, 95, 94, all the way down to 1. Now, of course, I can multiply those numbers in the top and bottom, but you see that the 99s are going to cancel, the 98's going to cancel, all the numbers down to 1's going to cancel, so really the only thing that you have left is just 100, because that's the only thing that didn't actually cancel. Do you see how much faster that is? When you look at this, I want you to not to look at it as I got to multiply 100 factorial and then 99 factorial. I want you to start to look at it as, what is going to cancel here? I have 100 multiplied all the way to 1. I have 99 multiplied all the way to 1. Even without writing all this out, you know the only thing left over is going to be a single 100 in the numerator. You're going to have to trust me. It's going to save you a lot of time because we're going to be doing this for every term of the binomial theorem here. Okay. Just to get another example, what if you have 10 factorial divided by 7 factorial times 3 factorial? Look at the form of this. 10 factorial divided by 7 factorial times 3 factorial. It is very similar to the form here. Something factorial times something factorial. Yeah, there's a minus, but forget about that. You have 1 factorial, another factorial on the bottom, 2 of them on the bottom. So of course I can multiply it all out and multiply it all out, but I know from experience here that on the top, the 10 factorial will be 10 times 9 times 8, 7, 6, 5, 4, 3, 2, 1. And on the bottom, it's just going to be 7 times 6, 5, 4, 3, 2, 1. So I know that everything 7 and lower is going to cancel. So in the top, after I do the cancellation, all that's going to be left is 10 times 9 times 8, because the 7, 6, 5, 4, 3, 2, 1 cancel with this 7 times 6, 5, 4, 3, 2, 1. All I'm going to have left is the 3 factorial, which is 3 times 2 times 1. So this is much faster than actually doing 10 factorial divided by 7 factorial times 3 factorial. In my mind, I cancel the terms that are basically all of the 7 factorial cancels out of there. And so on the top, you can actually multiply this out, of course, if you want to, 10 times 9 times 8, but then you realize I have a 2 and I have a 10. So 10 divided by 2 is 5. And I have a 3 and a 9, so I can cancel that. 9 divided by 3 is 3. So I'm literally taking 10 divided by 2 is 5, 9 divided by 3 is 3. And so all I have left is 5 times 3 being 15 times 8, and so I get 120. This is the final answer. Okay, I still may have to use a calculator, of course. I'm not saying that you can't use a calculator. I'm just saying that when you're writing these binomial terms out, you're going to have to learn how to cancel top and bottom, or else you're going to spend so much time writing factorials, it's going to hurt, basically. All right, so here we had some examples with numbers. Let's do an example with a variable, just to mix it up a little bit. What if you have n plus 1 factorial divided by n factorial? Now, some of you might be able to look at this and immediately tell me the answer, but if you're like me, you're not going to be able to do that. This is kind of like, you have an n on the top and an n on the bottom, so this is kind of like 9 factorial over 8 factorial, because if n is 8, then you have a factorial. Then n plus 1 would be 9 factorial on the top. It's like that. Or you could say, maybe it's like 6 factorial over 5 factorial. I can go on all day. Maybe it's like 3 factorial over 2 factorial. The top number is just one number bigger. So how do we simplify that? I mean, when it's numbers, it's very simple to cancel things, but what do we do when it's not numbers? That's the question. Here's the easiest way to do it. What is factorial in a sense? Whatever it is here, you just subtract 1 and then multiply, and subtract 1 more and multiply. So on the top, it'll be n plus 1, right? And then the next term will be 1 less than that, n plus 1 minus 1, right? And then the next term will be n plus 1 minus 2, because I'm subtracting 1 from this. And the next term will be n plus 1 minus 3, and then dot, 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 as far down as I want to go. Basically, like I do 9 factorial, it's 9 times 8 times 7. Here it's this minus 1, this minus 2, this minus 3. They're all multiplied together. On the bottom, it's n factorial. So it's n minus 1, n minus 2, dot, 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 because you're going to continue multiplying down there. Now, it doesn't look like this is very easy to deal with, but let's continue. N plus 1. What is this? 1 minus 1 is 0, so this actually just becomes n. 1 minus 2 is minus 1, so this is n minus 1. This is n minus 2 here. And what do I have on the bottom? I have n minus 1, n minus 2. And of course, there's more things multiplied here, but every term beyond is going to also cancel. You're going to have cancel, 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 so all you have is n plus 1. So this was one where it was variables with factorials, but we can still do the same kind of cancellation and get something here. Notice that this answer kind of makes sense, because we know that if we do 6 factorial over 5 factorial, this will be 6 times 5, 4, 3, 2, 1. This will be 5 times 4, 3, 2, 1. So everything will cancel except for the 6. So whatever's on the bottom, you just add 1 to it, and that single number is the answer. So whatever's on the bottom, we just add 1 to it, and that is the answer. So whatever n was, we just add 1 to it. That's what's the only thing that survives that whole process. So I really wanted to do a little review of factorial and do a couple of these simple problems, because when we start applying this thing, we are going to be dealing with that a lot. So our first problem, these problems are not going to be crazy. I mean, literally all I'm going to do is 2 more problems. The first problem is we're going to expand this thing using the binomial theorem, and then we're going to expand this thing using the binomial theorem. You already know what both answers are, so these are not trick questions. I just want you to see that the binomial theorem gives you the correct answer, and also so we can see with really simple problems how it works. And actually, even for simple problems, there's a lot of writing. So you have to be really careful to be slow and methodical. Okay, so what we want to find is a plus b quantity squared. Okay, now the first thing you need to do is you need to write, for every problem I want you to write the binomial theorem down. Every time. You have to write it down, and you have to substitute, and you have to put all the terms in place. If you don't write it down, you're going to make a mistake. Okay, so what is the binomial theorem? You're going to eventually memorize it. Here's what it is. It is k equals 0 up to n of n factorial, n minus k factorial times k factorial, and then you have a to the n minus k, and then you have b to the k. This is the binomial theorem, but in this case, n is, because remember, n is just whatever exponent I'm expanding by. That is the number that goes and slides into there. So the very next step is to take that you know that there's a 2 here and put it into the value of n here. So we say, next what we really have is a sum of k is equal to 0 up to n, which is now known to be 2. So you put a 2 in there. Here, n is 2, so it's 2 factorial. On the bottom here, it's 2, because 2 is n, 2 minus k. I know it looks weird, but that's what you have to write. Factorial k always stays the same. K is the thing that we're cycling through here, so you have to leave k alone. And then you have a to the n minus k, which will be 2 minus k, and then b to the k. So this is what you want to write. I want you to always write the binomial theorem down first, the way I wrote it down on the board, then substitute in. All I've done is put 2 in every location where I see an n. Okay? This is what I'm actually going to work from. So on the next line, we're going to start to expand. You just have to take it one step at a time. So first, k is 0. 0. So what do we have when k is 0? We go through here and we say, well, I have a 2 factorial in the top. Right under that, I have a 2 minus 0, because k is 0 factorial. And then k is 0, so I put 0 factorial here. Notice now I have only numbers in there, no letters. Then I have a to the power of 2 minus k, but k is 0. And then I have b to the k, but k is 0. Okay, notice that there's no variables anywhere other than a and b. When you start to plug in everything into the binomial theorem, you're going to calculate a's and b's and coefficients. There should be no n's and no k's after I write and substitute everything in. But we only did the first term because k is only 0 here. Now we do the whole thing again when k is equal to 1. So we put a plus sign because this is a summation. We're adding all the terms. K is now 1. You have 2 factorial. On the bottom, you have 2 minus k is 1 factorial, and then k is 1 factorial right here. I just put a 1 there. And then you have a to the 2 minus k being 1, b to the k being 1. Notice I haven't done any math. I'm doing that in the next step. I add to that the third term. Now k has been 0 and 1. Now k is going to be 2. Okay, so the third term, k is going to be 2. Again, we start with 2 factorial in the top, 2 minus k, but k is now 2 factorial, and then k goes here as 2 factorial. Okay, then we have a to the 2 minus k, but k is 2, so 2 minus 2, and then b to the k, which is 2. I know there's a lot of junk here. You just have to cycle through it. That's how the thing works, and that's why it gets so confusing sometimes. Okay, now we can actually start to evaluate things. Look at this first term. 2 factorial is just 2 times 1. Okay, 2 minus 0 is just 2. And again, it's 2 factorial. So I have a 2 factorial on the top and a 2 factorial on the bottom. Those are going to cancel completely. The 0 factorial, remember, 0 factorial by definition is 1. Okay, so basically what you have is, since the 2 factorial cancels with the 2 factorial and this is just a 1, all you have left out of that whole thing is just a 1. Okay, then you have a squared, and you have b to the 0, but anything to the 0 is 1, so it drops away because there's an invisible 1 here now. You put a plus sign, this plus sign, and you go evaluate the second term. Okay, you have a 2 factorial on the top, and you have a 2 minus 1, which is 1 factorial, and a 1 factorial. You know, 1 factorial is just 1, and 2 factorial is just 2 times 1 is 2, so you have a 2 over a 1. So all you get for the next coefficient is a 2. Then you have a to the power of 1, and you have b to the power of 1, like this. Now for the third term, what do you have? You have 2 factorial over 0 factorial, but 0 factorial is 1, and the 2 factorials cancel again. 0 factorial is 1, so this whole coefficient gives me a 1. Then you have a to the 0 and b to the power of 2. So your final answer is a squared plus 2 times a times b plus 1 times, this is 1, a to the 0 is 1, b squared. A squared plus 2ab plus b squared. Okay, a squared plus 2ab plus b squared. That's exactly what we get when we wrote it down in the beginning of the lesson, and that's exactly what you get if you do FOIL and multiply all those terms. Now, is the binomial a pain? Of course it is, especially for very small expansions, like to the second power. But what if you were doing an expansion to the 10th power? Then you would have a plus b times a plus b times a plus b times a plus b. You have to do that 10 times. And you have tons of multiplications, tons of terms, tons of addition, and sometimes tons of cancellations of terms. This is a pain, but it works every time for every binomial expansion exactly perfectly. And the beauty of it is you can program a computer to go through this loop and get all these terms and do it automatically. So we can use computers to calculate any expansion we want. So I wanted to do a simple one so you see how it works. You write down the binomial theorem as it sits. Then you take the exponent you have and you put it in everywhere you see an n, which is what we did in this step. Then you say k is 0 and put it in the first term. Then k is 1, make the next term. K stops at 2, that's the third term. Then you have to go through it and calculate the thing. Now what we want to do is the very next one, which is we want to get a little more practice by expanding something a little more challenging. A plus b to the power of 3. And you're going to see as we go through that not only are the terms different, but the coefficients are not, there's no 2 anywhere for any coefficient. So the binomial theorem is going to take care of all of that. And so that's what we are going to do. Okay. So the first thing is we want to write down the binomial theorem every single time. Trust me, if you don't write it down, you're going to make a mistake. Right, just like this. Then it's n, notice I'm copying it straight off my paper, n minus k factorial, and then a to the n minus k times b to the k. So that's what we have for the first part. And then for the next part, I do the exact same thing, but now I know n, which is the power, is 3. So I'm going to put that straight in there. And what I'm going to have is k equals 0 up to now 3. So now notice right away I'm going to have k is 0, then 1, then 2, then 3. I'm going to have 4 terms in this expansion instead of 3 like before. And then you already know we're going to have 4 terms, so that makes sense. N factorial means on the top it's 3 factorial over. Here we're going to have n is 3 minus k. K always has to stay in there. Factorial times, again, k factorial. Then we have a to the 3 minus k. Then we have b to the k. All right, lots of stuff here. How do we proceed? K is now 0. We cycle in and we put 0 everywhere for k. We say 3 factorial over 3 minus 0 factorial, then 0 factorial, putting k being 0 for each of those locations. A to the 3 minus 0, b to the 0. That's the first term. Now we add to that, k is now 1. We stick that in there. 3 factorial over, here k is 1. 3 minus 1 factorial, 1 factorial for k right here. Then we have a to the 3 minus 1 and b to the 1, putting k is equal to 1. You see I'm going a little faster as I go because you kind of get the hang of it. Also notice I'm not doing any math. I haven't multiplied anything. Most of the challenge is just putting in and writing all this stuff down, honestly. Then what we have, k is 0, k is 1, now k has to be 2. So we're going to have this guy here, 3 factorial, k is now 2, 3 minus 2 factorial, then this k is 2 factorial. Then we have a to the 3 minus k being 2, then b to the k is also 2. So just put a 2 in for all of these locations. And then we'll do our last one, k is 0, k is 1, k is 2, now k has to be 3, and then we stop. We have 3 factorial here, then we have 3 minus 3 factorial, then 3 factorial, then a to the 3 minus 3, because k is 3, and then b to the power of 3. So now we've finally written everything down. what do we get? Now here is the thing. In the previous problem, I was able to, in my head, do a lot of these divisions here to get the coefficients, because it was just 2 and factorial and 0 factorial, and it was very easy in your head. But what you're going to figure out is that when you go up in the complexity, you should not be doing any math in your head, and you really should just write everything down. So notice that I could calculate what this is, but instead I'm going to be really careful, especially when I get to the middle terms, to not make a mistake. Here I have 3 factorial. This is 0, 3 minus 0, so this is also 3 factorial. They're going to divide away, and then you have 0 factorial, which is 1. So my leading term is 1. Then I'm going to have a cubed, and b to the 0 is 1. So that's my first term. This next term, what I'm going to have is a 3 factorial on the top. What am I going to have on the bottom? 3 minus 1 is 2 factorial times 1 factorial. But 1 factorial is just 1, so it's 2 factorial times 1, so it's just 2 factorial. So just write it as 2 factorial. 3 factorial over 2 factorial. I know that we could do this in our head, but if you do too many things at once, you'll make a mistake. So just simplify things and just leave it like this for this next step. Then you're going to have a squared b to the first power. Then we're going to have this term. We're going to have 3 factorial. 3 minus 2 is 1 factorial. I can throw that away, but I'm going to have a 2 factorial on the bottom. 1 factorial is just 1 times 2 factorial. So I have a 2 factorial right there, like this. And then I'm going to have a to the power of 1, b to the power of 2. Last term, 3 factorial divided by 0 factorial, which is 1. And then 3 factorial is going to cancel here, so you're just going to have a 1. And you're going to have a to the 0, b to the power of 3. All right, let's see what we got. The final answer is a cubed plus 3 factorial over 2 factorial. Remember, this is 3 times 2 times 1, and this is 2 times 1. Everything's going to cancel except for the leading 3. A squared b. B to the first, just write it as b. Same exact thing here, same exact term. Everything's going to cancel except the 3. Then you have ab squared, Then you're going to have 1, a to the 0 is 1, b cubed. So let's check ourselves. A cubed plus 3a squared b plus 3ab squared plus b cubed, which is exactly what we got when we wrote it down. If you were to multiply these out and cross-multiply all the terms, you get exactly the same thing. So now that you have actually done a couple of problems, I'm hoping you can see what the binomial theorem is doing. Okay? The very first part here, this junk, is just calculating these coefficients. The 1, the 3, the 1. In the previous problem, it was different coefficients. These guys here are just, as k increases, it's making the power of a go down, down, down. And it's making the power of b go up, 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 which is exactly what you see. A is going down, down, down to 0. B started at 0, and it's going up, up, up to a maximum of 3. The sum of the exponents in this case is always 3 because my expansion was a third power. And exactly the same pattern followed in the previous example that we did. One thing I'll say as I close the lesson is this is how I'm writing the binomial theorem. It's the way that I think is the easiest way to see what's going on. There are other ways to write the binomial theorem down. In your book, you might see it written slightly differently, slightly different notation, slightly different way of writing these coefficients, but ultimately they're all going to produce exactly the same math when you write them out. So if your book has a very slightly different equation, I mean, you can use it, that's fine, or you can use this one, that's fine. It's all the same thing. They're slightly different ways of writing different things. So make sure you can solve these yourself. I really want you to do these problems, even these simple ones here. That helps you understand how to apply this binomial theorem. Then follow me on to the next lesson. We're going to crank up the complexity a little bit more and solve some more problems with the binomial theorem.